Hello everyone, I'm Subhasree Patro, and today I'll be talking about fine-grained complexity via quantum walks. This is a joint work with Harry Buhrman, Bruno Loff, and Florian Speelman. Let's begin. Of late, a lot of money and effort is going into quantum computing. That is because for many computational problems, we have quantum algorithms that are faster than the classical ones, and rightfully so. Because quantum computers are a more powerful model of computation than the classical computers. However, we also see that quantum speedup is not guaranteed for all problems. Let's look at some examples. For problems like integer factorization and discrete log, we have quantum algorithms that are exponentially faster than the classical ones. But for problems like triangle finding, orthogonal vectors, three sum, CNF SAT, the quantum speedup that we see is only polynomial. And for surprisingly, for problems like longest common subsequence, edit distance, and freshet distance, we don't even the current quantum algorithms are as bad as the classical ones. So it would be nice if we could, in any way, know for which problems we have a quantum speedup, and if there is, then how much. But the state of the art is not so bad. There are some problems like unordered search where the quantum speedup is known to be optimal. But for some problems like traveling salesman problem or CNF SAT, the speedup is not known to be optimal. And in some other cases, for example, like the case of recommendation algorithm, we thought we had an exponential quantum speedup, but it turned out that we did not. So the natural question again to ask is how much quantum speedup is possible, and how do we assert that? Another line of direction, an unfortunate result was that with this current known quantum error correcting techniques, there is no quantum advantage for problems having only quadratic quantum speedups for any practical input sizes. This was a recent result by Babush et al. But now, how can we show then that for what kind of problems the best possible quantum speedup is, say, quadratic? And we will soon see that we can do so by proving lower bounds. For example, there are several computational geometry problems for which Ambinis and Larka in 2020 gave almost linear algorithms showing that a quadratic speedup for these problems was possible if you use quantum computers as opposed to classical ones. And using our techniques, we are able to show that conditional on some reasonable conjectures, the algorithms that Ambinis and Larka gave for these problems are actually optimal. And again, invoking this recent result by Babush et al., uh, we can then see that for problems such as these computational geometry problems, it quantum computing is not going to help much, at least in the near term future, unless there is some significant improvement in the error correcting techniques. Now, the results that we prove here use a family of technique called fine-grained complexity. But let me also bring to your notice that fine-grained results in the quantum setting has been given for other problems, such as closest pair problem, edit distance problem. But all these results are fairly new, and they just date about 1.5 years ago. But now I have been using this term lower bounds, and I will be using these terms upper bounds and lower bounds also in my talk in future. So let me briefly explain what upper bounds and lower bounds mean in complexity theory. Now suppose you have this computational problem and someone says there's an upper bound for this problem. Now upper bound for any problem is just the runtime of the best algorithm that solves the problem. While lower bound, on the other hand, is the time required for any algorithm that solves the problem. And we say the bounds are tight, or we say the upper bound that we have is the best algorithm when the upper bound and lower bound match for the problem. But the unfortunate situation is that we do not know how to prove lower bounds. So how do we know whether the best known, like whether the upper bound that we have is optimal or not? So we resort to a technique called fine grained reduction. Though it is fairly recent in the quantum setting to prove fine grained results, it is uh, 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 it's a very common, not common, but it's a old method known in the classical setting. But let me just briefly describe as to what fine grained reductions look like. Okay. Now let's say we have this problem A, which is very well studied. A lot of people have put effort in it, but for some reason it has the reputation of being hard. People are not able to improve or not able to find fast algorithms for problem A. And now suppose there's a problem B, which is interesting, but has not been studied as much as problem A. And people don't know how hard it is to solve problem B. Then can we can we make any statement or can we get any knowledge about the hardness of problem B based on what we know about problem A? And turns out that we can if we are able to reduce problem A to problem B. Now, what do I mean by reduction? A reduction is possible if if I'm able to map these input instance of problem A to some input instances of problem B, and using an algorithm for problem B, I can solve actually problem A. Then I say we have a reduction from problem A to problem B. Now, how is this going to help us? Now, it's going to help us in this way. Suppose there was a faster algorithm for problem B, then using this faster algorithm for problem B, we can get a faster algorithm for problem A, which we do not believe is possible. That means there is no faster algorithm for problem B. So what we have done is we have got a lower bound for problem B based on a believed lower bound for problem A. Let me summarize again. So we pick a problem A, which is believed to be hard. We try to reduce problem A to problem B. Then we conclude lower bound for problem B using the believed lower bound for problem A. And for the purpose of this talk, we picked the problem A to be three-sum problem, and we ended up proving lower bounds or conditional lower bounds for computational geometry problems and for zero edge weight triangle finding problem. Now let me give you a flavor of what three-sum problem looks like, especially given that this becomes our central problem in proving certain lower bounds. So this is a very uh, easy problem to describe. We have this list S of n integers, and all we want to know whether or not there exists a triple ABC belonging to this list such that they all sum to 0. Let's look at an example. This is a list of 6 integers. And we can see that if we set a equals to 1, b equals to 4, and c equals to -5, we have this triple which add up to 0. Now, what do you think will be the classical complexity for three-sum problem? So clearly there's this trivial n-cube algorithm where you take all these n-cube possible triples and check if any of these triple has this solution to threesome. But there's also a slightly less trivial n-square algorithm for this. Let me briefly show you how. Now take this list S, make a copy of it. That will cost you n time. Now make a third copy, but this time sort the third copy. So this requires additional n log n time. Now what we do is we go over all these n square pairs from the first two lists, and we would like to see if there exists an element in the third list that is negative of some of these, negative of some of one of these pairs. Okay. And because this third list is sorted, we can do a binary search to search for such an element. So the total time complexity for this part becomes then n squared log n. And in fact, there's an other trick that we could use to even improve this n square log n time algorithm to actually give us a n square algorithm. Now, the surprising part is people are not able to improve on these n square algorithm for threesome in the classical setting. They have come up with some polylogarithmic shaving off, but that's about it. So it was, and for the purpose of this talk, we are going to ignore any polylogarithmic factors of n. So it was ultimately natural to conjecture that threesome requires n squared time on a classical computer. But what use could this be of? It was in fact of very good use because based on this conjecture, lower bounds for a lot of problems were being able to establish. And that gave explanatory power as to why people were not able to improve on the existing algorithms for a lot of problems. But let me slightly zoom in and show you how, give you a flavor of how these reduction look like. Okay. So let's pick this reduction from threesome to zero edge weight triangle finding problem. So we have this threesome problem, which we have already defined. And we have the zero edge weight triangle finding problem. This is also an interesting problem where we are given a graph of n nodes with weighted edges, meaning every edge has a weight associated with it. And what we would like to know is if there is a triangle whose weight, sum of the weights of the edges sum to 0. And what this reduction implied is if there was an n subcubic algorithm for zero edge weight triangle finding problem, then threesome could have a subquadratic time algorithm, which is based on this threesome classical conjecture not believed to exist. So the zero edge weight triangle finding problem cannot have a subcubic algorithm as long as the classical threesome conjecture is true. And the reduction was actually a two-step reduction where threesome was first reduced from threesome to a sorted version of threesome. By here, I don't mean the usual sort that we talk about, not the one that where the elements are sorted in ascending order, but in some sort of a structuring, some sort of a general sorting that threesome is reduced to. Okay? But this general sorting also requires, how to say, n log n or just linear amount of time. Okay? And then a non-trivial reduction from sorted threesome was given to this zero edge weight triangle finding problem. But why are we talking about this classical thing? We are all quantum people, so we should talk about all these in the quantum setting. So now let's look at the quantum algorithm for threesome. Is it possible that for threesome, given that quantum computers are more powerful than classical computers, it's possible that maybe threesome has a faster than classical algorithm, right? Maybe threesome has a faster quantum algorithm than the classical one. In fact, it turns out to be true. Now let's look at the same algorithm that we discussed, the classical one for threesome. So we have this list. We have one copy sorted. So we have taken additional n log n time. And we have this other two copies of this list. But now what we do is, instead of using the classical algorithm that goes over all these n square pairs and checks for an element whose sum exists in this list with a negative sign, we actually Grover over this n square tuples. And because Grover search is quadratically faster than classical one, we are able to um, do this entire, we're able to quantize this entire classical algorithm in n log n time. So now, given that we are not able to find any other faster classical algorithm, and given that that is a conjecture in the classical setting as to threesome requires n square time, it is natural to conjecture that threesome requires n time on a quantum computer. And uh, in a paper by Ambinis and Larka, uh, this conjecture was also informally stated. But now, what happens to all these lower bounds that we concluded based on these classical reductions from threesome to these computation geometry or sequence problem or dynamic problems or triangle connection or any of these? So let's look at this reduction from threesome to zero edge weight triangle finding problem again. So we had this linear reduction from threesome to sorted threesome. And we had this non-trivial classical reduction from sorted threesome to zero edge weight triangle finding problem. And now we would like to see if any of that still holds. Now, what we noticed is the reduction from threesome to sorted threesome is not at all trivial to port quantumly. But fortunately, the non-trivial classical reduction from sorted threesome to zero edge weight triangle finding problem was because it was local, we are able to actually quantize that very easily. So now we would like try to fix the other thing or give a whole new reduction from threesome to zero edge weight triangle, right? So we thought, okay, why not? Why not try and fix this part? So and the other thing that we also noticed that was not just not just the reduction from threesome to zero edge weight triangle, even the reduction from threesome to a vast collection of computational geometry problem involved a similar intermediate step, where threesome was supposed to be first reduced to some version of sorted threesome, and then the sorted threesome or some version of sorted threesome was to be reduced to uh, to all of these problems. But we don't know how to quantumly reduce threesome to sorted threesome. That is because sorting in the classical setting requires n log n time, but sorting in the quantum setting also requires n log n time. So there is no sublinear sorting algorithm for input for us in the quantum setting. That's why the classical reductions fail in that particular step to be directly ported into the quantum setting. And we give a workaround for that, and we show using a quantum walk technique that the sorted version of threesome are equally as hard as threesome in the quantum setting. And this is what we are going to do now. But a disclaimer here. This is a very technical part of the talk, and uh, people who are not very familiar with the quantum walk query algorithm to solve threesome might find it a little difficult to follow this part. Now, recall the quantum walk based query algorithm for threesome problem. So what is the setup? We have this Johnson graph with parameters n and r, where r is some n power beta, where beta is between 0 and 1. So basically, r is a polynomial of n, but it's a sublinear polynomial in n. Okay. Now, each of this vertex represents an r-sized subset of this instance of threesome problem. And we have edges connected from vertex vi to vertex vj only if it differs in exactly one index. Okay. And the nodes that contain solution to threesome problem are considered to be marked. Now, what the quantum walk algorithm does is it tries to find this marked node in an optimal number of queries. Now, please note, I'm talking about queries right now. Okay? So the complexity of the walk algorithm turns out to have a nice formula of this form, with S being the setup cost, N and R in this product, C being the checking cost, and then U being the update cost. Now, again, note that when I mean complexity of this walk algorithm, this value holds for both the query algorithm and for the time complexity as well. But now again, we are back to query algorithm. So let's just talk about the query complexity. So what we noticed is um, there we can solve this threesome. We have a query algorithm that solves this threesome problem with setup cost being set to R, the checking cost is 0, and the update cost is 2. But let me also explain. I'm sorry, I forgot to explain what this setup cost, checking cost, and update cost even mean. So the setup cost is actually the cost of storing all these queries for every vertex, and that is done in superposition. So it is only seen per vertex. Okay, and as there are R elements in it, in about R order R number of queries, we are able to store all these query values for every vertex. Now the checking cost is the number of queries required, and the checking cost in terms of query is the number of queries required to check if a particular node is marked or not. Now, in this case, this checking cost is 0 because once we already have the queries, we are not going to query the Oracle again for the input for checking whether a node is marked or not. We can always refer to the queries that are already stored and we can just check that. And the update cost is the number of queries required for you to change, for you to traverse from one node to another, basically for one step of the walk. So you're basically changing two elements. So that's why two queries. But what about the time complexity of this walk algorithm? Oh, by the way, also one more thing. So this query algorithm turns out to be optimal with, and the query algorithm also turns out to be sublinear, which is n power 3 by 4, and it is optimal by a lower bound given by Beloff's. Anyway, now coming back to the time complexity. What about the time complexity? Now, if we try to use the same algorithm and try to look at the time complexity, what goes wrong is, yes, we are able to do the setup in almost linear, almost our amount of time. We are able to even achieve this update with, almost constant time. Now, this tilde over O or tilde over O here just means there are polylogarithmic factor. But we are not able to reduce this checking cost any further. Now, an interesting idea would be, what if we are able to store this R size subset in some structured way that, you know, we can probably check this vertices, like the queries and the vertices, in a faster way. Is that possible? And it turns out that using some dynamic data structures, and such dynamic data structures exist, we can actually store these query values in every node in a ascending order. And that the data structures are also so efficient that they allow the data structure operations like insertion or deletion or indexing to happen in polylogarithmic amount of time, which for us anyway are the factors that we don't care about. So now that we can use this dynamic data structure to sort these elements and keep it. So instead of calling the threesome, so for the checking algorithm subroutine, what we will now end up calling is a sorted threesome subroutine for every vertex. And because we'll be doing it in superposition, uh, it's pretty fine. Now, let's assume that sorted threesome is easier than threesome. And what do I mean by easier? So till now we saw that threesome didn't have like at least we believe that threesome doesn't have a sublinear quantum time algorithm. But let's say sorted threesome is easier. And let's say sorted threesome has a sublinear quantum time algorithm. Then by plugging in the values in the equation with, the same equation, but let me address it by t, this s being almost linear in R, c strictly sublinear in R, and this update time being same, that is almost constant, because we are ignoring the polylogarithmic factor, we see that this total value of this expression actually can be made sublinear, which means a sublinear algorithm for sorted threesome can be used to give a sublinear algorithm for the original threesome in the quantum setting. But that is not supposed to be possible unless quantum threesome conjecture is false. So to repeat, if threesome requires linear time, then sorted threesome also requires linear time on a quantum computer. This is what the result we get. In fact, using the same technique, we are also able to comment on the quantum hardness of some other structured version of threesome problems. Like here in this example that I discussed, it was the sorted threesome that I explicitly talked about, but we are also able to give a slightly more general version of this sorted threesome problem. And because of our proof strategy, we are now able to port the classical reductions from threesome to this zero edge weight triangle finding. And we are able to also quantize the classical reductions that exist from threesome to this vast collection of computational geometry problems. And as a result, as a result, we were able to prove a tight linear lower bound. Yes, it is conditional, but we are able to prove a tight linear lower bound for zero edge weight triangle finding problem. And we are also able to prove a linear lower bounds for this list of computational geometry problem, for most of which the bound is tight, but there are some open problems which are not yet closed there. And to summarize, uh, we see that fine grained reduction is a promising way forward to be able to prove superlinear lower bounds. To be more precise, what it is able to prove are the lower bounds that are beyond the query lower bounds. Okay? And using our proof strategy, we are able to assert the hardness of sorted versions of threesome, which, though it is very trivial to prove in the classical setting, it was uh, not at all trivial to quantize those results in the quantum setting. And the last result is a bit cynical, but nevertheless, it's an important result because for many problems in computational geometry, we are able to show that the speedup that we can get in the quantum setting is at best quadratic, which means because of this recent result by Babush et al., we are not able, like in the near term future, quantum computers might not be a good bet for these computational problems. And the future directions for our project are also numerous. We still have a lot of these reductions in the classical setting, from threesome to sequence problems, or threesome to dynamic, or threesome to triangle collection and matching triangles, that are yet to be explored in the quantum setting. And we believe our proof strategy is going to help us a lot there. But these are still things that are open. And also, for many computational geometry, not many, but there are these 4 computational geometry problems here for which we have linear lower bound, but we do not have linear upper bound yet. And so that is still an open problem until Either we improve the lower bound, or we get some better algorithms. And finally, to conclude, we believe quantum fine-grained complexity opens an interesting way to prove conditional time lower bounds, and especially for problems which have super linear algorithms, this seems to be the best way forward. And I would like to thank you for the attention. Thank you.